Good morning. Hi, I'm Zach with HKN, and today we're going to make a video about power in circuits that have maybe some impedances that have complex values. You can see we have some kind of black box looking resistors here. They have an imaginary part. So we're going to see if we can solve something in the circuit with that. This is it's actually a common problem. Inductors and capacitors will have imaginary impedance. So we run into this in real world scenarios. So what we're going to do today is first we're going to find the average power dissipated in this resistor R, and then we're going to find the average power delivered by the current source. So average power. So okay, so see we have a source here that is, this little squiggle denotes that it's a sinusoidal source. And the only information that's actually given to us about the source is its amplitude and its phase shift. So we can reason that it's oscillating at a constant frequency, right? And so everything in the circuit, everything else in the circuit, all the other values in the circuit, maybe say the current through here, the voltage across there, that will all be oscillating at the same frequency. So since we have a common frequency, we kind of just ignore that it's there. Then how would we find average power? Well, instantaneous power would be given by V times I, V any time t times I any time t. But we can integrate that over some time and then divide it by that amount of time to get the average. And someone has already done all that work for when our instantaneous V and I are sinusoids. Maybe they're sinusoids with different amplitudes and different phase shift, but oscillating at the same frequency. We get that this integrates to 1/2 Vm, which is the maximum value of the oscillating voltage, Im, which is the maximum value of the oscillating current, and times cosine of the phase of the voltage minus the phase of the current. So if there's a phase difference between them, say the phase angle of the voltage is a little more than the phase angle of the current, we'll have a positive term in there. We'll see that when we do the problem. So let's try to find first the average power dissipated in this 10 ohm resistor. So what would we need to know? We'd like to know the voltage across the resistor and the current through it. So let's see if we can figure out the current through it. So we have a current source here, and so all this current supplied by the source is flowing in this branch, and then right when it gets to this node right here, it has to split in between these two branches. And we know a little trick from probably earlier in circuits class called a current divider. And we can, okay, so I'll just draw a simpler scenario real quick. So if we have a current and we have two resistors it could possibly go through, R1, R2, we'll say this is total current. We say that the current through, let's see if we can figure out the current through R2, or yeah, so we'll call it I2. So I2 by the current divider rule will be equal to the total current times this resistive branch, R1, over the sum of the two, R1 plus R2. Now that gives the current through R2. So you see we picked, as the numerator, we picked the opposite resistor than the one we're looking for the current through. So that can be extended. So I use just R's there, but that can be extended to impedance values where we have complex valued. Yeah, really these are complex valued resistors. You can think of them like that. Ohm's law still works. All the principles we learned with just resistors works. So let's find what the value of this current is when it splits. So how do we do that? We have and what are we going to call this? We could call this I2. We'll call this I1. And we'll call this IS. That is not an S. Okay, so let's see, I2 would be equal to IS times Z1, right? Impedance of that branch over the impedance of both branches. So how are we going to do that? So these, this resistor and this impedance are in series, so we can just add them together to get the total resistance for this branch. And then we would add that number to this. So we'd have Z1 plus 10 plus Z2. So that will give us the value of I2 there. So let's expand this out some. What is IS? IS is magnitude of 3, phase shift of 40 degrees. And we want to multiply that by Z1, which is 7 plus J3. All of that is going to be divided by. Okay, so what would Z1 plus 10 plus Z2 be? That would be, so with complex numbers, when we have them in rectangular form, we'll have a real part and imaginary part, and when we add them together, we can just add the real parts, add the imaginary parts. So what would 10 plus Z2 be? That would be, 10 is entirely real, right? So we would just add that to the real part. That would be 19 plus J2. And if we look down here, what we're actually looking for is the sum of all of them. So we have 19 plus J2 plus 7 plus J3. So we'll add the real parts and the imaginary parts of that, and that will get to be 26 plus J5. Okay. So now we have a kind of weird setup here. We have this is a complex number right here as well. It's just in a different form. So actually, let's draw that real quick. So if we have plane where this is real and this is imaginary, and we have some value, we can express this as a real coordinate, call it X, and an imaginary coordinate, we'll call it Y, or we can express it as a radius or a length with a angle theta. So those are just two equivalent expressions of the same number. So these are both valid forms of a complex number. So what we do to solve a thing like this, we can do it by hand, but it's a little bit hard. We type it into the calculator, and it does all the work for us. And depending on what mode you have the calculator in, it'll spit out a complex number in that mode, but it'll take numbers in either form. All right, so when we type this into the calculator, I had my calculator in polar mode, so this becomes 0.8629 amps with a phase shift of 52.31 degrees. So that's not that wouldn't be very easy to get just doing this by hand. So you almost have to use a calculator for this. All right, so we have a current. So that's not what we're looking for, but it'll help us in finding what we're looking for. Okay, so we have the current. Actually, we found the current through this branch. That's good because we were looking for the power dissipated in this resistor. So now we have the current through it, and we'll find the voltage across it as a result of this current. Okay, so Ohm's law holds for numbers in this form and complex numbers, right? So to get the voltage across this, we could just multiply this current we found times the resistance. So what was this? Yep, this is I2. So let's say that the voltage here, let's call it VR. VR is equal to the resistance times the current through it, and what is that? That'd be 10 times I2. And that would be equal to 8.629. And okay, so when you multiply a complex number by a constant, we could think again of this being a a radius at a certain angle. When we multiply it by a constant, we change the radius length, but we actually don't change the angle at all. It doesn't do anything to the angle. So we would have the same angle and the amplitude multiplied by 10. 52.31 degrees. Okay. So now we have, what do we have? We have a value for current and voltage. Current through the resistor, voltage across it. What else do we need to, we don't need anything else actually. Okay, so let's calculate the average power in it. Now, this little term here, I have a VM, an IM in there. Those are the maximum value, maximum amplitudes of these values, and that is actually this part of the number. The maximum amplitude is the length of your phasor. So we have all the information we need. So let's calculate that. We'll say that the power average in the resistor is equal to 1/2 times Vmax. What's Vmax? 8.629. Times Imax. What is that? That is 0.8629 times cosine. Cosine of the angle of the voltage minus the angle of the current. And what do we have here? We have a scenario where they have the same angle, right? So this angle minus that angle would be 0. And what is cosine of 0? That's 1, right? So this term goes to 1. This all solves to 3.723 watts. So that is the average power dissipated in our resistor. So something interesting we could kind of see from this. So when two phasors have the same angle, we say they're in phase. So the current through a resistor is always going to be in phase with the voltage across it. And so this term right here will always be cosine of 0. So that tells us, indirectly sort of, that the power in a resistor is always, we always have entirely real power in a resistor. We'll never get a power that has some phase angle. Okay, so the same is not necessarily true for when our load is complex. So we'll do that now. We'll go to part B. We got to find the average power delivered by the source. So what's a good way to go about doing that? We would need the current delivered by the source and the voltage across the source to get the power in it. So what would be a good way to find the voltage across the source? We know how much current it's putting out. We could combine all this to be an equivalent impedance and then multiply that by the current to get the voltage, right? So let's do that. This can be combined, again, it can be combined just like we would combine normal resistors using the same math. So how would we do this if they were just resistors? We'll call it Z anyways. So how would we start? So we see we have two impedances in parallel, in series there. So we would add them together, right? To give us the equivalent of this branch. So we would have, actually, let's do it symbolically for a minute, just to keep things more simple. We're calling that R. We have R plus Z2. That would give us this branch, and then that equivalent would be in parallel with this, right? Parallel with Z1. So that would give us our equivalent. Could we keep this going a little bit? What is R plus Z2? It's 19 plus J2, right? We just add the real parts together. That in parallel with Z1, which is 7 plus J3. Okay, so also the little trick we know from when we have two resistors in parallel will work for here. We take the product over the sum to get the equivalent. So we would type into our calculators 19 plus J2. When you do these, they work like normal numbers, but make sure you keep them inside parentheses. Less room for error that way. Multiplied, and at the bottom we sum them. 19 J2. Okay. So what do we get when we type that in? Earlier I got that this was 5.495 with a phase of 18.3 degrees. Okay, so we have, that's ohms. So we have a complex valued impedance, right? In the real imaginary plane, it's at an angle, so that means it has an imaginary part. But that's okay. We're used to dealing with that. So that is saying that this circuit is equivalent to this source with just one impedance at that value. So if we had that, how did we get the voltage across it? We could just multiply the current value by this impedance value. We'll call that Vs for the voltage across the source would equal to, let's see, current through the source times the equivalent, right? That'd be equal to 3 with a phase of 40 degrees times this. Now, okay, so we talked a little bit earlier about when we have the rectangular form of complex numbers, it's pretty simple to add them together because you just add their real parts, add their imaginary parts, and that's your answer. It's kind of the same with polar form. Multiplication is relatively simple, multiplication and division. With polar form, we multiply their magnitudes to get the new magnitude, and we add their angles to get the new angle. So this comes to 16.486 with a phase shift of 58.32 degrees. Okay, so that is the value of the voltage across our source. That would be this voltage from here to there. So now we have everything we need to get power by the power delivered or absorbed by the source. We're gonna guess that it's delivered. So how would we do this? Well, the convention says that power convention for a current source would be that, actually the power convention for any element is that we take the current through it to be the current coming in to the positive terminal, right? So for a current source that has this voltage across it, the current coming in to the positive terminal would be the negative of the current that the source was putting out. Does that make sense? So that's going to give us a negative number, and that's actually okay because in power convention, negative power means it's being supplied, and that's kind of what we'd expect this to be doing. So actually, I'll just leave that. So what would we get with this formula? So P average in the source be equal to 1/2 V max. What is V max? V max is this magnitude of this voltage here. 16.486 times I max. But what did we just say about this? So we know this source is sending current this way at 3 amps with a phase shift of 40. But for our convention, we want the current coming into the positive terminal. So it's going to be the negative of this. Now, like we said earlier, we multiply by a constant. We multiply polar form by a constant. We just multiply its amplitude. Right, so we're going to multiply that by -1. This will be -3. So that'll be I max. And we need this term. So this time we do have a difference in phase between these two values. So what is theta V? That's this angle right here in our number. So what would that be? 58.32 minus the phase of the current. Now what is the phase of the current? You see it's here. It's 40 degrees. Okay, so now we have our entire term written out for average power. And when we type this into a calculator, we got that this was equal to -23.476 watts. Now, like we guessed before, it was going to be negative, and that makes sense because that means it's supplying power. It's the only power source in the circuit, so it's going to have to be supplying the power. All right, so that's it for today. Thanks for watching. We'll see you next week.